In this video, we're going to identify functions given a set of points or a graph. We're going to determine domain and range of relations and functions, and we're going to learn about function notation. Let's take a moment and review a few things here. We're going to evaluate these expressions given x equal 4, y equal -2, and z equal to 0. Every time that you substitute, I recommend using parentheses. So 4 times -2 squared minus 6 times 4 plus 3. Using parentheses every time you substitute will cut down on a multitude of mistakes that students tend to make. Another mistake that's common here when simplifying is to try and multiply 4 times -2. When you think of the order of operations, you remember, please excuse my dear Aunt Sally or PEMDAS. Parentheses is first. Well, this parentheses scenario is multiplication, and that comes well into the order of operations. When they talk about parentheses, they mean inside the parentheses, is there anything to evaluate? Since this is just a number of -2, there is nothing inside to evaluate. So we move to exponents, which is an exponent of 2. So we square what's inside the parentheses first. A -2 times -2 is +4. And that it will be multiplied by 4. -6 times 4 is -24 plus 3. 4 times 4 is 16. -24 plus 3 is -21. And 16 minus 21 is -5. In number 2, 5 times z, which is 0 squared minus 7. Again, 0 squared we do first, which is 0 times 5. 0 times 5 is 0 minus 7 is -7. Okay, so just some quick review here, evaluating expressions. Now on to some vocabulary involving functions. A relation is any set of ordered pairs, whether that's a list of ordered pairs, a table of values, a graph, anything like that is a relation. And the domain of that relation is the set of all of the first components, or x values usually, and the range would be the y values, all of the y values. In a domain or range, if those values are repeated, you only need to list them once if asked for the domain or asked for the range. And you'll see some examples of that in a little bit. A function now is more specific than a relation. It's a case where each first component, or x value, can't write today. Each x value corresponds to exactly one second component or y value. Another way to say this would be, for each x there is only one y, or the x values will not repeat in a relation for it to be a function. So we take a look here at example 1. For each relation, give the domain and range, and then determine if it's a function or not. Alright, so the domain. And we generally write these in ascending order. So -3, 0, 1, 5 are the x values. And all of the y values would be a part of the range, again in increasing order. negative 2, 2, and 5. Notice the 2 repeats in the y values. That is okay, but we don't need to list that positive 2 twice. We can just list it once. Now, is this a function? The y value of 2 did repeat, and that is okay. It is the x values that must stay the same, or it must not repeat. So we have a negative 3, a 0, a 5, and a negative 1. I'm sorry, a positive 1. Those are all different, and therefore, yes, this is a function. 1b, the domain. Negative 3, 0, 5, and another 5. So I don't need to write that a second time. While we're here talking about the domain, we see that this x value of 5 is repeated. So I know this is not a function. And we can come back now and list the range. Negative 2, 2, and 6. Taking a look at function notation now. Functions are denoted as f of x equals. The f of x is how we say that takes the place of the y. So f of x equals x squared minus 3 would be the same thing as y equals x squared minus 3. F of x is read that way. You could also say f evaluated at x, and that in some ways is a better way of thinking about this, because what it means is, when you're evaluating f of 3, you would substitute 3 in the equation into every single x, in place of every single x, and then simplify as we did in those review questions earlier. The y value is dependent because it depends on what x value you substitute in. And that x value would be independent because you could pick any x value. Why do we need function notation is a great question to consider. And what I'll tell you is it helps us, particularly in systems of equations, which you will see often in business or in computer programming, among other fields. There are multiple equations in a particular problem, and by using function notation we can label them. So like there could be a profit equation, so we could call that P of x equals something, and then a cost equation, C of x, and we could compare those things. Many other applications here, or needs for the function notation, once you get into systems of multiple equations in one computer program or one problem. In the next couple examples, they're very similar to the review questions at the beginning, where we were evaluating functions given certain values for the variables. Well, here it's exactly the same, except we're using the function notation. First, find g of 3. So find function g, there it is, and substitute 3 in for every x. Negative 7 times 3 squared plus 3. Again, remembering to use parentheses every time we substitute. 3 squared is 9 times negative 7 and you get negative 60. We will now find g of negative 4. So we substitute a negative 4 in every place that we see x. Negative 4 squared is positive 16. And negative 7 times 16 is negative 112. Minus 4, negative 116. Example 3 now gives us the function h of 3. So, or h of x equals 3, sorry. So h of negative 5 equals 3, and there's no x on the right side of this equation for us to substitute a negative 5 into. So h of negative 5 equals 3, and the same point, h of 1,000 equals 3. Or any x value I substitute in to this function, I'm going to get an output of 3. Let's think about this graphically. It is going to be a horizontal line through the y value of 3. Y equals 3. It does not matter what x is, the answer or the output is always going to be 3. Example 4. P of a. We're going to substitute the variable a in for x. Negative 4a plus 2. Perfect. And you might think that was silly that we even did that, but really I want you to see that you could substitute expressions or variables, not just numbers, in to a function. For example, now p of b plus 1 equals negative 4 times b plus 1 plus 2. Now we have something more to do. We have to distribute the negative 4 to both terms inside this parenthesis. Negative 4b minus 4 plus 2. And combine like terms, negative 4b minus 2 would be the simplified expression for p of b plus 1, or p evaluated at b plus 1. This is going to set a foundation for composition of functions later, and how I present that. Continuing with example of 5, we have t of x equal to the square root of 5x minus 1. Why don't you hit pause and try this example. Once you have an answer, go ahead and hit play and see how you did. T of a equals the square root of 5 times a minus 1. And that's great. There's nothing else to do. We really just replaced the variable of x with a variable of a. But here in this next one, t of c plus 2, we have some more work to do in the simplification steps. 5 times c plus 2 minus 1. Okay, so we're going to distribute the 5. 5c plus 10 minus 1 is 5c plus 9, and we still have the square root. There may be a temptation for you here to take the square root of 9 because that is a perfect square, But because it is part of this binomial, there is a plus sign here. We cannot take the square root of parts, individual sections or terms. So we are finished at this point. The square root of 5c plus 9. Vertical line test is something that can help us determine, if given a graph, if a relation is actually a function. And how the vertical line test works is that if you can draw a vertical line through the graph and it will only intersect the graph at one point, then you have a function. If it intersects at more than one point, then you do not have a function. That was weird. There we go. The domain of a function is all possible values for x, and again, the range of a function is all possible values of y. So we take a look at the example 6. Determine if the graph is a function and identify the domain and range. Okay, so we can graph this line here and draw a vertical line through it. We see that it crosses only one time, and you could pick any vertical line to run through this. It is only going to cross one time. So yes, it is a function. The domain is all possible x values. So I like to think of this graph, or the x-axis here, as like a magnet that will draw every point from the line directly to it, straight down or straight up. Is there any x value along this axis that would be uncovered? And the answer to that, in this case with the line, is no. So the domain is all real numbers, or from negative infinity to infinity in interval notation. The range the same, but this time we look at the y-axis as that magnet, kind of drawing every single point back towards itself perfectly horizontally. Not that my lines are perfectly horizontal here, but if it drew all of those points back to the y-axis, would any part of the y-axis be uncovered? No. So the range is also all real numbers. Looking at example 6b, we see this sideways parabola and we draw a vertical line through it. It crosses more than one time, so this relation is not a function. The domain, however, starts at 0 and goes to the right, or positive values here. So from 0, which is included, to positive infinity would be the domain, and the range, as we see, this continues to extend upward and downward. All real numbers will be covered in the range of this function. Not function, this relation, excuse me. Why don't you try letter C and letter D on your own? Go ahead and hit pause. Unpause once you have completed this, and then check to see how you did. I'm going to draw a vertical line through this ellipse. See that it crosses twice, so this is not a function. The range is all of the y values between -2 and 2. And those values are included. It could be 2 or -2. And it looks like the domain, or possible x values, are from -4 to 4. Inclusive again. Letter D, draw a vertical line. It crosses one time. Yes, the absolute value curve is a function. Its domain, as the entire y-axis is covered, is all real numbers, or from negative infinity to positive infinity. And the range is from 0 to positive infinity. 0 is included all the way to positive infinity. There are no negative y values in this graph. Taking a moment here to look at the domains of functions specifically. Again, the set of all values that would satisfy x are the domain, the x values of the function. If the denominator equals 0, or if there is an x value that makes a denominator 0, that value would not be included in the domain. Or if there is a negative number underneath an even-powered radical, square root, a fourth root, a sixth root, for example, we cannot take an even root of a negative number. So those really are the two restrictions that we're mainly looking for at this level. And so a couple examples with that. Here I have a variable, I see it in the denominator, so I need to find what value of x would make the whole denominator equal 0. Often students see the variable of x in the denominator and just say that x can't be 0. But if we substitute 0 in for x, we have 0 minus 2, which is a denominator of negative 2, not 0, and that would therefore be okay. So instead what I like to do is to take x minus 2, the whole denominator, and set it not equal to 0. Add 2, and we find that x can't be 2. If we use interval notation to represent this domain, that would be from negative infinity to 2 not included, union 2 to positive infinity. This would be how we would write this domain in interval notation. In set builder notation, the set of all x such that x is an element of the real number set where x cannot be 2. Either one of those are appropriate ways of writing that domain, including the restriction. For function g here in example 7b, we have a square root. That is an even-powered root, and we cannot have a negative number. So 3x plus 2 must be greater than or equal to 0. Otherwise, it would be negative. So we subtract 2 from both sides. 3x is greater than or equal to negative 2. We divide by 3. X is greater than or equal to negative 2/3. In interval notation, and I'm going to put that up here so I have space, you would say from negative 2/3 to positive infinity, and that is inclusive of the negative 2/3. In set builder notation, the set of all x such that x is an element of the real number set where x is greater than or equal to negative 2/3. Again, either way of writing that would be acceptable. Function h has a square root, so an even-powered root, meaning I cannot have the expression underneath that radical be negative. It has to be 0 or greater. But then the radical is in the denominator, so because it's in the denominator, it can't be 0. So in this case, we'll take 7x plus 4 and say that it's greater than 0. We subtract 4, 7x is greater than negative 4, divide by 7. X is greater than negative 4 sevenths. Interval notation, let's get a little more space. Negative 4 sevenths to infinity, and we're not including negative 4 sevenths. That's just a boundary here. And in set builder notation, the set of all x such that x is an element of the real number set where x is greater than negative 4 sevenths. Why don't you try letter D, looking at finding the domain of function p. Go ahead and hit pause, unpause the video when you're ready to check. X squared minus 3x plus 2. This particular function or relation has no denominator, and there are no even-powered roots. So we have nothing that could be restrictive of x, and therefore the domain is all real numbers. And this, for example, is a parabola. That's the shape of the graph, which will continually get wide. So moving left and right, covering the entire x-axis eventually, and it will continue to move upward, therefore covering all y values greater than this minimum y value right here at the vertex. But we're not concerned about the range, just the domain in this question. Since all real numbers is the answer, they're all included as possibilities. In interval notation, it is negative infinity to positive infinity. In set builder notation, it is the set of all x such that x is an element of the real number set. And that's it. There is no further condition since all real numbers are included. Hopefully this video gives you a better understanding of domain and range, as well as whether or not a function or a relation is a function, whether given a graph, a table of values, a set of ordered pairs, or an equation.